Very well. Welcome back, everyone. Let us finish up chapter 8, then we're going to start chapter 9. So in chapter 8, 8.3, we start talking about relations, and now we're interested in some important relations. Well, recall that we defined a relation as a subset of Cartesian product between two sets. A relation like R is a subset of Cartesian product between two sets. Also recall that when we have a set and that set has some subsets that are mutually disjoint from each other, and the union of those subsets is equal to set A, we name it a partition. So let A be a set, a partition for set A is a collection of subsets. Subsets A sub 1, A sub 2, A sub 3, and the rest of them, which are non-empty sets of non-empty sets, with these two conditions that, first of all, A sub I intersection A sub J is empty. It means that they are mutually disjoint. If you take two random subsets and if you find an intersection between them, that intersection is empty. Second of all, the union of AIs is A. So if you take the union of these AIs over I, it is equal to A. So recall that we can visualize this scenario. Here you have set A, and you have some subsets, non-empty subsets, A1, A2, A3, and so on. This is a partition for this set. We call that for Z, for example. Z can be divided up into two sets, even numbers, odd numbers. They have no intersection with each other. And also, if you take the union of all even and odd numbers, it's going to be equal to Z itself. Well, today we're going to introduce this idea that if we have a partition, we can actually define a relation. We can define a relation using a partition. The terminology that we use is we can induce a relation using a partition. Relation induced by partition. Induced or generated by partition. Well, okay, how does it work? We're going to define this relation this way. First of all, suppose you have a set. Let A be a set. You're going to define a relation this way. We're going to say that for all X and Y in A X is in relation. X is in relation with Y if and only if we can find a partition. We can find a partition in set A such that, so we're taking one of, you can find one of these subsets. You have a partition, you can take one of these subsets such that this X and Y belongs to that subset. So X is in relation with Y if and only if there is a subset like A sub A such that X and Y, both of them, lands here in this subset. So between all of these subsets, you can find one of them such that X and Y, they both land in that subset. In this case, we say that, hey, there is a relation that is induced by that partition. Very well. So we have a theorem here. This theorem says, well, now that you've defined this relation induced by partition, it happens that this relation is an equivalence relation. Theorem. The relation induced by a partition is an equivalence relation. What's the meaning of that? It means that that relation is symmetric, reflexive, and transitive. And transitive. Okay. So now let us talk about equivalence relation, like M being congruent to N modulo a number like D. Definition. I've seen this before, but the official definition, the official name is definition of congruence mod D. Very well. Suppose you have two integers. Let M and N be two integers and D be a positive integer. And let D be a positive integer. Remember that we had this definition divisibility. We said that, hey, D divides M minus N. The definition was if and only if there exists another integer like K such that in this condition, M minus N is equal to D times K. Well, it happens that if you have divisibility, D divides M minus N equivalently, there exists an integer like K such that M minus N is equal to dk. You can write it another way. We can write this as M is congruent with N mod D. If you divide M by D, if you divide N by D, the remainders are the same. For example, we're saying that saying that 12 is congruent with 7 mod 5. Okay, it's very easy to verify. By definition, since 12 minus 7, so 12 is your M, 7 is your N, and 5 is your D. Okay, 12 minus 7 is equal to 5, and 5 divides 5, of course, that makes sense. Or you have this case, or, okay, if I divide 12 by 5, the remainder is equal to 2. Okay, let's see. If I divide 7 by 5, the remainder is equal to 2. So this is another approach verifying that 12 is congruent to 7 mod 5. They have the exact same remainder when we're dividing both of these by 5. The same. Very well. So remember equivalence relation. When you have an equivalence relation, instead of listing all of the elements that belong to that relation, you're using some representatives for that relation. What do I mean by that? Okay. Suppose we have a set and we define an equivalence relation on that set. Definition of equivalence class. So let A be a set and R be an equivalence relation on A. Okay, we define equivalence class this way. We define an equivalence class this way. You say that, hey, equivalence class of A is equal to the set of all elements in set A such that X is in relation with A. So let us read it this way. Equivalence class, this is equivalence class of A is equal to the set of all elements in set A, members of A, such that those members are in relation with A. X is in relation with A. Okay, give us an example. What are you talking about? I'm just going to give you a very easy example. Okay. Let A be equal to Z. Talking about integers. Okay, we have integers, and I'm going to define, let's say, divisibility by 2 on Z. Divisibility by 2. But I'm going to say, hey, m is congruent to n mod 2. What's the meaning of that? It means that 2 divides m minus n. Well, okay. Simply, I can say that, hey, m is equal to 2k plus n. And you can just write this guy down as m equals to n is just an integer. Am I right? So m can be written as 2k plus 0. M can be written as 2k plus 1. M can be written as 2k plus 2. M can be written as 2k plus 3. So it includes all even and odd numbers. Even and odd numbers. Okay. Very well. So now I'm asking you to write down the equivalence class of, let's say, 2. Also, I ask you to write down equivalence class of 3. How do you represent these two? Equivalence class of 2 is the collection of all elements in Z, all X values in Z, such that X is in relation with 2. And the equivalence class of 3 is going to be the set of all X values in Z, such that X is in relation with 3. You can use a different letter, it doesn't matter. You can use Y. If you want to avoid any confusion, you can change X into Y. Very well, okay. What's the meaning of that? It says, well, X belongs to Z such that X is in relation with 2. X is in relation with 2. Let me define this relation with divisibility by 2 this way. Saying that, hey, 2 divides A minus X, or A is equivalent, is congruent to X mod 2. You can rewrite this way as well. Okay, perfect. So X is in relation with 2, and this relation is divisibility by 2. So divisibility by 2, but going back to divisibility by 2, what's the meaning of that? It means that if you take any number and you divide it by 2, the remainder is equal to 0. So if 2 divides n, so it means that the remainder is 0. Okay, perfect. So how do you define this relation this way here? Divisibility by 2, and this is R. So what are the collection of those numbers that we have? We say that, hey, X is in relation with 2. What are the elements that are in relation with 2? It means that if you take those elements and divide them by 2, the remainder is going to be 0. So what are those numbers? X is in relation with 2. We can say that, hey, 2 is one of the options, of course. 3, no. What about 4? Of course. How about 0? Yeah. What about negative 2? So plus minus 2, those are the options here. Plus minus 4, plus minus 6, 0, and the rest of them. So it's going to be the collection of all even numbers. What about the equivalence class of 3? It says all of integers that are in relation with 3. But the relation that it defined is divisibility by 2. It means that if I divide them by 2, the remainder is equal to 0. Okay, well, What are the elements that are in relation with 3? If I divide them by 2, the outcome is going to be, the remainder is going to be 0. So how do we list the elements here?